Hi, I'm Puya Nixiar, and today I'm going to talk about the thermal sensor and data acquisition systems. For thermal sensor, I'm specifically going to talk about the thermocouple with the amplifier and thermistor. So let's start to see what the data acquisition system, or DAQ for brief, is. So traditionally, if we wanted to measure quantity, this quantity could be temperature, we were using a thermometer. By the advent of the computers, nowadays we are using the data acquisition systems to do the measurements for a couple of the reasons. First, the computer are really fast. As an example, if I want to measure the temperature in the combustion chamber, where temperature goes up from 20 degrees of the Celsius to the 200 degrees of the Celsius in just less than 1 second, so a person is not able to do such a fast measurements to track the temperature change. But with the computers, we are able to do the measurement every 1 millisecond or every 1 microseconds. Also, with the computer, we can connect the multiple sensors to the computer and do the measurement simultaneously on all of those sensors. In addition to these, also we can store the data in the computer for the future use. Okay, so let's take a look on what the data acquisition system is. So these are the components of the data acquisition system. So the first step is the sensor. Here it's a thermocouple for measuring the temperature. The sensor is connected to the DAQ board. DAQ board is connected to the DAQ card, and DAQ card is in the computer, which is in connection with the main board. And finally we have a software, which is here LabVIEW, which is the interface between the computer and the user. Alright, let's take a look at the DAQ system setup. Here we see thermocouple is connected to the DAQ board. DAQ board is connected to the DAQ card in the case of the computer. And then in the final level we have a software, which is LabVIEW. LabVIEW has two parts. One part which is called the control panel for writing the program, and one part which is called the front panel for showing the results. So the point regarding the sensors I want to mention is, so for measuring different quantities we have a different sensors. These quantities can be a temperature, they can be pressure, velocity, accelerations, or the displacements. So 90% of these sensors, they are working in a way that when they are measuring different quantities, at the output they are producing the voltage, or they are manipulating the voltage at the output. So in next slide we are going to look at the thermocouple and to see how does the thermocouple, when placed in a different ambient with a different temperature, is produce different voltage. Alright, so let's look at how does the thermocouple works. The thermocouple is working with the Seebeck effect. I'm going to explain the Seebeck effect with analogy in the thermodynamics. Imagine I have an enclosed container and I've placed some water in this container. So at the initial stage there is no vapor molecules here, and the liquid molecules start evaporating and filling this area. After some time I noticed that the level of the liquid has been dropped and the vapor molecules has filled this region, and the level of the liquid is not dropping any further. So there is equilibrium between the liquid phase and the vapor phase. But at the microscopic level, if I'm looking at the interface, I see that the liquid molecules are evaporating to the vapor phase, and also the vapor molecules are condensing to the liquid phase. So there is active transfer between the liquid phase and the vapor phase, and as the number of the molecules are evaporating is equal to the number of the molecules of the vapor that condensing, so in a macroscopic level I have equilibrium. So the same thing happens in the metals. In the metals we have free electrons that they are moving randomly in any directions. If I'm considering any interface, as there isn't any current in my metal, so the number of the electrons are going from down part to the upper part is equal to the number of the electrons are going from upper part to the down part, and there is no net current in the metal. But what happens if I'm hitting one side of the metal? When I'm hitting the one side of the metal, I'm increasing the velocity of the free electrons in these regions, so the electrons in the hotter part are going to move faster. Again, if I'm considering an imaginary interface or surface, Now this time the number of the electrons are moving from down part to the upper part is bigger than the number of the electrons are moving from upper part to down part. So I would have a net migration of the electrons from the hot region to the colder region, and when there is a net migration of the electrons, it creates a current, and when there is a current across the resistance, it produces the voltage. So the voltage produced here depends on the type of the metal we are using. As an example, copper is producing a stronger voltage than the iron or the nickel. So they have taken advantage of these phenomena and they have made a thermocouple. Thermocouple is simply just two different metals connected at one point. We can see here, this is an example of the T-type thermocouple. The copper and constantan are soldered at one end. So what happens if I'm placing this end at a different ambient with different temperatures? So hotter region here, colder region here, one voltage has been induced in this part. Also the same thing happens here, one voltage has been induced in this part. So as I have a stronger voltage in this region, I would have a net voltage in the direction of the stronger voltage, and by placing the thermocouple in a different ambience, so I've been able to get and produce and create the voltage at the output, which its magnitude is a function of the temperature. If I'm placing hotter temperatures and higher temperatures, so I'm getting a stronger voltage. Another point I want to mention is we place this end in a different ambience with a different temperatures, and we connect these two other ends to the DAQ board. So when we are using a thermocouple, we want to know what the CJC value is. CJC value stands for the cold junction compensation. And as we are connecting these two ends to the DAQ board and the DAQ system is in the room, so these are approximately the room temperatures. So we saw how by placing the thermocouple at a different temperature, we were able to create a voltage at the output, or the thermocouple was producing and creating the voltage at the output for us. The next sensor we are going to consider is a thermistor. Thermistor is a thermally sensitive resistor. So let's see how does it works. The thermistor is just a resistance, that is resistance is function of the temperature, which is connected to another resistance in a series, and they are connected to the power supply, which is most of the time is a 5 volt. Example is here. This is a thermistor is connected to this resistance in a series, and this goes to the positive of the power supply and this goes to the negative of the power supply. So if we are using the Kirchhoff's rule and we write it here, we can obtain the relationship between the voltage across the thermistor and the resistance of the thermistor. If we increasing the temperature, the resistance of the thermistor would drop, and the voltage across the thermistor also would drop too. So this is called a negative temperature coefficient thermistor, or NTC thermistor. We also have a positive temperature coefficient thermistor, that when we are increasing the temperature, the resistance would increase. But the NTC are most commonly used in industry and the laboratories. So for a thermocouple, we observed putting the thermocouple in a different ambience, we were getting the voltage at the output, and the thermocouple was producing the voltage for us. But here we provided the 5 volt voltage, and only changing in the ambient temperature caused that the voltage across the thermistor would be changed. So in another word, thermistor just is affecting the voltage and is not creating any voltage for us. The voltage at the output of the sensor goes to the computer, and now we want to look at how the computer stores this voltage. We need to first define the resolution in units of the volt. The resolution in units of the volt is defined by the voltage range given by the sensor. The thermocouple, as an example, have a very small voltage range in the range of the negative 1 millivolt to the positive 1 millivolt. The thermistor has a bigger voltage range in the range of the negative 5 volt to the positive 5 volt, and then divided by 2 to the power of the n. N is the number of the bits of the systems. So I want to explain and talk about the bit a little bit. So the bit is the smallest unit of the memory of the computer, and it can have two different states, 0 or the 1. In a very early computers, the bit was shown by the lamp. when the lamp was on it was showing 1, or when the lamp was off it was showing 0. Or in another form of the memories, it was a paper with a different cells, so if the cell was punched it was showing the 0, and if the cell was not punched it was showing the 1. In now this computer it's a transistor. If the transistor has a voltage it's showing 1, and if it doesn't have a voltage it's showing 0. So by having the n number of the bits I can get a 2 to the power of the n different combinations. As an example, imagine I have a 2 bits, so I can have a 4 different combination. How? The first cell can be a 0, the second cell can be a 0, and this is the first combination. The second combination can be a 0, 1, the third one 1, 0, and the last one 1, 1. So by having the n number of the bits I can have a 2 to the power of the n different combinations. Alright, so let's now consider our sensors and the DAQ systems. Okay, imagine we have a 1-bit DAQ system, and this is the output of the sensor. Imagine we have placed the sensor in a combustion chamber. The temperature has gone up from 0 to 100 degrees of the Celsius in a specific time. So as I have a just 1-bit system, I have a 2 different combinations, 0 and 1. So I consider the voltage I'm receiving from the sensor from 0 to 1. I'm going to show that with the first combination and consider that as a 0 volt. And if the voltage I'm getting from the sensors is from between the 1 and 2, I'm going to show that with the second combination and consider as a 1 volt. So how did my DAQ system is going to store this data is something look like this. So from this time interval, all the voltage between the 0 and the 1 they have been stored as a 0 volt, and in this time interval all of the voltage from 1 and 2 have been stored in a 1 volt. Now I see that the continuous voltage from the sensor has been stored in a computer in a discrete manner. So this is called the analog to the digital converter, because it's converting a continuous voltage to the discrete voltage, and this is because how are the computer working and how the computer are storing the information. What happens if I'm increasing the number of the bits of my system? So with the 2 bits, if I have a 2-bit, I have a 4 different combination, and these are the combination. I consider if the voltage is between 0 and 0.5, I'm showing by the first combination and consider that as a 0 volt. If between 0.5 and 1, I'm going to show that with the second combination and consider as a 0.5 volt, and the other one the same way. So how the output at my DAQ system would be, and how the computer is going to store these data in this way. In this time interval it's going to consider that as 0 volt, in this time interval consider as a 0.5, and the two other in the same way. As we see, by increasing the number of the bits, so the output voltage at my DAQ system has a better accuracy, and it has been distinguished between the data more. So if I keep increasing the number of the bits of the system, the final output data stored in the computer is going to get closer and closer to my main data from the sensors. To compare two different sensors, we still cannot use the resolution in units of the volt to compare them, because as having the higher number of the bits is beneficial, having the bigger voltage range is also beneficial. So to compare two sensors, we need to consider two more criteria. The next one is a sensitivity. Sensitivity, by the definition, is a change in output to the change in input. More sensitive sensors, it means when we are changing the input. As an example, we are changing the temperature 1 degree Celsius, the output voltage of the sensor would change significantly. But the less sensitive sensor, it means when we are changing the 1 degree Celsius at the input, the output voltage of the sensor does not change that much. So let's consider this example to elaborate more. Imagine I have a less sensitive sensor and I have a 1-bit DAQ system. I've placed my sensor in this ambient temperature and I've got this as the output of the sensor. Both of them in my DAQ system are going to be stored as a 0 volt because both of them are below 1 volt. Now I have a more sensitive sensors. I have placed my sensor in the same ambient temperature and I've got this voltage at the output. No, these are going to be stored as a 0 and 1 volt at in my DAQ system. Now we see, although we had the same DAQ system, by using a more sensitive sensor, we were able to distinguish at the output when there was a change in the temperature of the input. But with the less sensitive sensors, we see the system could not track and trace the change in input and consider both of them as the same temperature. The example of the increasing the sensitivity of the sensor is a thermocouple with the amplifier. We see here a thermocouple simply connected to the amplifier. So what the amplifier is doing, just amplifies the output voltage of the thermocouple. The thermocouple produces a very small voltage range at the output. The voltage the thermocouple is producing is in the range of the negative 1 millivolt to the positive 1 millivolt. And by using the amplifier brings the voltage in the range of the negative 100 millivolt to the positive 100 millivolt. So what's the advantage of this? Let's take a look at this example. Imagine I've placed my thermocouple in the two different ambient with a two different temperature, and it has given me this voltage. If even I have a 2-bit system, my 2-bit system would store them, both of them, as a 0 volt. But if I use amplifier, and just imagine in this case the amplifier multiplies the output voltage by 10 times, so I would have a 0.4 volt and a 1.1 volt. If I give this to my 2-bit system, at the first case I get a 0 volt, but at the second case I get a 1 volt. We see how by increasing the sensitivity or amplifying the output voltage of the thermocouple, now we have a better measurement of the data. In this case, two different temperatures, the system could not distinguish between the temperatures and just store both of them as a one value. But here our system has a better accuracy of the measurement. Two different temperatures, also we have a two different voltage at the output. Finally, when we want to compare two different sensors, then we need to consider the resolution in units of the Celsius in case of the thermal sensors. And the resolution in units of the Celsius is defined, and the resolution in units of the volts, as we talked before, divided by the sensitivity. What does this resolution show? This resolution shows the smallest increment the sensor has. So when we have a sensor with a smaller resolution, it means they are accurate and they are able to measure, record, and track a smaller change in the temperature, pressure, whatever quantity we are measuring. Okay, so right now we talked about the sensor, the DAQ system, and we saw how the sensor are producing the voltage and how this voltage has been stored in the computer in a discrete manner. But there's one question. I've placed my thermocouple in ambient and it has given me a 0.5 volt. How can system knows what temperature this 0.5 volt is showing? The answer is the system cannot understand what the temperature this voltage is showing, and we should tell the computer what this voltage is, what temperature this voltage is showing. So we tell this to the computer by giving the relationship between the voltage and the temperature. So we need a curve or a relationship to give it to the computer, and the next question is how we can find such a relationship. The simplest answer is by measurement. We get that sensor, put in one ambient, we measure the output voltage of the sensor, we measure the temperature of the ambient by thermometer, and then repeat these for a different ambient temperatures and measure the corresponding voltage at the output, and finally connect these kind of the points to each other and find the curve, and then give that curve to the system. When the system has that curve, when we place the sensor in a new ambient and it gives as an example 1.2 volt, so the computer brings that 1.2 volt to here, then goes to this curve and reads the corresponding temperature from this curve and shows at the output. So this process calibration. The calibration is to giving the relationship between the voltage the sensor is producing and the temperature or other quantities, can be pressure, acceleration, velocity, whatever exists between that quantity and the voltage. So this process is called calibration. Taking too many points is really time consuming and it's very costly. So we usually do not do this. And we are just skipping this very tedious procedure. And what we are doing, imagine this is my temperature sensors, this black line, the real behavior of the sensor. I've obtained this black line by doing 1 million measurements and connecting those points to each other, which shows the relationship between the voltage the sensor has produced at the different temperatures. But doing those measurements is very time consuming and costly. What I'm going to do, I'm going to just consider 2 points. I'm doing the measuring the temperature at the one specific ambient and also measure the voltage my sensor is producing at that specific ambient. Again, I'm going to do the measurement with that sensor in the new ambient with the new temperature, also measuring the voltage of the sensor at that new ambient and connecting these 2 points to each other and obtaining a line, then giving this line to the computer. So what happens? So it means when I'm giving this line to the computers, it means I have calibrated my sensors. It means now the computer knows what's the relationship between the voltage the sensor gives to it and the temperature that voltage is showing. So next time when I'm placing my sensor in a new ambient and the sensor producing the voltage, the computer comes to this curve and find the corresponding voltage, draws a line to the red one, and then shows these TC at the output. But because I've approximated the real behavior of the sensor with a line which was not a linear, the real behavior is not linear, we see the real temperature for this voltage is TR, not TC. So this is called the calibration error. I can decrease and reduce this calibration error by considering more points for calibration. As an example, if I take it 3 points for my calibration and I do the quadratic calibration, this error will be reduced. Or I can consider and get the 4 points and do the cubic calibration to reduce this calibration error further and further. Another criteria to compare different sensors is how fast they are responding to the change in the environment. As an example, imagine we are going to measure the temperature change in a combustion chamber where everything happens in just less than 1 second and temperature goes up from 20 degrees of Celsius to 200 degrees of Celsius. So if I don't have a very fast sensor like sensor 2 here, so which takes around 20 to 25 seconds to respond to the change in environment, so I would not be able to track the temperature change accurately in the combustion chamber. So sometimes for a specific application we want to choose a very fast sensors, and to be able to pick up the appropriate sensor we have a criteria which is the time constant. So how does we can find the time constant for different sensors? We need to find the initial value and the final value and find that the way between the initial and the final value. Then we should go ahead and find a 63% of this path